Hello class, welcome to Coronachem day 21, May 4th. And what I'm going to do today is review the test you had on April 28th, if I'm not mistaken. Yeah, April 28th. So it was comprised of 4 questions from the text. They are numbers 1014, 1034, 1066, and 1086. I've got the first 2 questions written up on the board and I'll explain it to you. So the first question, 1014, asks, the compound 1-iododecane, a non-volatile liquid with a density of 1.2 grams per milliliter. The density of mercury is 13.6 grams per milliliter. What do you predict for the height of a barometer column based on 1-iododecane when the atmospheric pressure is 752 torr? The key to answering this question correctly is to realize that the column height is inversely proportional to the density of the liquid. That means if the liquid is denser, then the column will be shorter. That's why they use mercury for barometers. Mercury has a very high density, so it makes for a barometer with a very reasonable column height. If you used water in your barometer, and water only has a density of 1, your barometer would have to be 33 feet tall to record atmospheric temperature. You can pull a column of water to a height of 33 feet with a perfect vacuum. Why does that happen? Why does a column of water rise up a straw? It's because you suck out the air into your lungs, and by creating a deficit of pressure on the water inside the straw, the water pressure outside the straw pushes the water up into the straw. So it's a question of transfer of momentum. The transfer of momentum from the atmosphere on the outside of the straw is greater than the transfer of momentum from the air inside the straw, and therefore the water level rises until the weight of the water column equals the force exerted by the transfer of momentum. When those 2 amounts are equal, the column stops rising. The highest you can raise a column of water on the surface of the earth is around 33 feet, because that's the weight of the atmosphere as predicted by the kinetic molecular theory. Now, if you use the denser liquid, that same pressure is exerted by a shorter column. That's why we use mercury. Mercury is 13 times the density of water, so the height of the column will be only 1/13 the height that you would get with water. So with that in mind, we set up an equivalence, but remember to flip it. So 1.2 over 13.6 is in inverse proportion to the column height generated with the 13.6 grams per milliliter density liquid versus x height of the iododecane. Do a cross multiplication to solve for x, and we get 8,522.6 millimeters, which, if you divide by 1,000, turns into a column height of 8.52 meters. That's the final answer right there. That question was out of 9 marks if you showed all the different steps in the calculation. 1, 2, 3, 4, 5 for this assumption, and then 3 more marks for the last bit. The second question, let's see if we can get that whole thing in frame. Perfect. Is 1034. So 1034 asks, a neon sign is made of glass tubing whose inside diameter is 2.5 centimeters and whose length is 5.5 meters. If the sign contains neon at a pressure of 1.78 torr at 35 degrees Celsius, how many grams of neon are in the sign? The volume of a cylinder is pi r squared h. So of course we're assuming that the tube is a cylinder, and here's the volume for a cylinder. V is equal to pi r squared h. Let's convert all the units to centimeters to make so that we only have 1 unit at the end. So pi times the radius. So why did I put 2.5 divided by 2? Because they give us the diameter, but we need the radius. So half of the diameter equals the radius, centimeters, all squared. By all squared, I mean you square the number and you square the unit. This is the height in meters. Let's convert that to centimeters by multiplying by 100. So that turns into 1.25 all squared. This turns into 550 centimeters. Again, multiply everything together. My calculator initially says this, but you can press a button that converts that number, 859 and 3/8 pi. You press this one here. If you have the same calculator as I do, it says change. So by pressing change, you get it to report that number that way. So that's 2,699 centimeters cubed. You see here, you square the centimeters. That's centimeters squared for that part, and centimeters there. So centimeters squared times centimeters to the power of 1 gives you centimeters cubed, which is a volume, which is what we're looking for. Then we converted it to liters because our gas equation, we're going to use the liter version, the liter atmospheres. So that's the volume of our tubing. Now I converted the pressure to atmospheres, so 1.78 torr over 760 torr per 1 atmosphere. So that's the pressure in atmospheres. There's the volume that we just finished calculating. There's the gas constant in units of liter atmospheres per Kelvin mole. Here's the absolute temperature, meaning you've added 273 to the Celsius temperature. Here's the Celsius temperature. You add 273.15 to that to give you the Kelvin temperature. And if you look at the units, atmospheres cancel, liters cancel, kelvins cancel, and then you get an answer which is moles in the denominator of the denominator, which puts it as a numerator, because the denominator of a denominator is the numerator. So the answer is 2.5 times 10 to the minus 4 moles. Neon has a molar mass of 20.17 grams per mole. Moles cancel, and you get an answer in grams. You get 5.04 times 10 to the negative 3 grams. I multiplied it by 1,000 to put it into milligrams. You don't have to do that last step. I just did that for the sake of practice. If you left this answer 5.0 times 10 to the minus 3, that was fine. But it's in grams. If you put it in milligrams, you get 5 milligrams. Okay, that was your final answer. That question was worth 20 marks. Every little step was 1 mark, so it adds up to 20 check marks when you're done. Now for the fun part, erasing, and the next 2 questions. So let's do that here. I found by accident that the best way to erase this board is to first use water. Well, you could try dry erasing. That doesn't work very well at all. It sort of just fades it. All it takes some of the ink off, so that doesn't work very well at all. So I started using a sprayer. Take off the first part, and then I noticed that a damp cloth and alcohol tends to take off the rest of it. So I discovered the best technique. I did buy a dry erase board yesterday, or on Friday, but something happened and didn't seem to come through. But I think it's much better to use a dry erase board because the phone is literally 2 feet away from the fridge, and I barely have room to walk in between. I need a little bit of breathing room. Most of you got your tests done, which was nice. Got another month to go, so let's keep pushing together. I see that some of you are taking your time watching the videos when I post them, but that's okay. I don't care as long as you get around to it. But don't get too relaxed, because chemistry doesn't teach itself. You gotta actually keep working at it. Even I start forgetting if I don't work at it. There's a lot of little details that are easy to forget. Now here's the trick I discovered by accident. If you use a little alcohol, a little bit of alcohol on the fridge there, and then wipe down again, you get the last little bit off. I mean, it doesn't have to be completely spotless, you'll still see fine, but you know. Okay. Question 3 asks, and it's 1066 in the book. It asks, what are the mole fractions of each component in a mixture of 5.08 grams of oxygen and 7.17 grams of nitrogen and 1.32 grams of hydrogen? Most of you got the first half of the question right, but a lot of you made the same little silly mistake. I'll show you what you did. So this question is probably going to take the whole fridge. So the first step is to find how many moles you have of each of the different things. So we had 5.08 grams of oxygen, which has a molar mass of 15.394 grams per mole. So that means you have 0.1587 moles of O2. Now I had all 8 decimal places in my calculator, but I'm not going to write them all out on the fridge because there's just not enough room. And then 7.17 grams of nitrogen divided by the 2 times 14.0067 grams per mole of nitrogen. So that gives you 0.2559 moles of N2 glasses. And you had 1.32 grams of hydrogen divided by 2 times 1.00794. You'll notice all the gases here were diatomic, and if you don't know that, you're going to make a mistake right there. But luckily, I've taught you well, and you know your diatomic elements. Because nobody made that mistake. I was quite proud of you that you did. Nobody made the mistake of putting monatomic. All of you knew that they were diatomic elements. You knew your Hofbrinkel. So you get 0.6548 moles of hydrogen. And then if you add them all up, you're going to get 1.0695 moles of gas. We'll just say gas, because it's all these. Remember, Avogadro's hypothesis says it doesn't matter which gas you have, they're all going to have the same volume at standard temperature and pressure. That's not 100% true, but according to ideal gas law, it's close enough. Now, if you want to find the mole fractions, you're going to take this number of moles and divide it by this number, 1.0695, and you're going to get, so I'm just going to write mole fractions. Okay, and for this one is 0.148. For this one, it's 0.259 divided by 1.0695 is going to give you 0.239. And for this one, it's going to give you 0.612. These are all the mole fractions. And so if you use the law of well, let's find out what the pressure exerted by all these gases is going to be. All right, so we're going to say P total is equal to nRT over V. I'll start off with PV equals nRT, and then I transpose the V down there. And you get 1.0695 moles times the gas constant 0.082057 liter atmospheres per Kelvin mole, and then the temperature is 273.15 plus 15 Kelvin, because it's absolute temperature that you're looking for, and then the total volume is 12.4 liters. I think it was given in the question. So what you get for the total pressure is 2.0393 atmospheres. Now, how do you find the partial pressure of each gas? The partial pressure of each gas is directly related to the mole fraction of each gas. So the way you say that is P, let's say O2, partial pressure O2 is equal to the mole fraction of O2 times the total pressure. Okay, and what you get there is 0.148. That's the mole fraction. Now, some of you, what you did is you took this number, okay, And you were lucky you even got close to the answer because it turned out that the total was 1.06, but it's wrong. You got to take the mole fraction. The mole fraction is number of moles of the gas divided by the total moles of gas. So you see, because the numbers were close, you guys got close to the correct answer, but the concept was wrong. I only deducted 4 marks. I probably should have deducted more because it shows that you don't really understand what's going on. But anyway, let's hope you get it this time. So 0.148 is the mole fraction for the oxygen. Total pressure is 2.0393. So the partial pressure of oxygen is 0.303 atmospheres. Same calculation for nitrogen. Partial pressure of nitrogen is equal to the mole fraction of nitrogen times the total pressure of all the gases. So you get, actually it's not 0.148, it's 0.239 for nitrogen times ditto for this part, same number, and you get 0.488 atmosphere. And for the last one, partial pressure of hydrogen is equal to the mole fraction of hydrogen times the total pressure of all the gases. Partial mole fraction of hydrogen is 0.612. And total pressure ditto to that one, and what you get is 1.25 atmospheres. Okay, so that would be your, whoops, I didn't show you, there it is. Okay, here's the actual thing I wrote out. If you want to pause it or take a screenshot and then enlarge it after. That's the second half of the problem. Here's the first half of the problem if you're really stuck and you don't like my writing on the fridge. Okay, now the last question was 1086. 1086 asks, it turns out van der Waals constant B equals 4 times the total volume actually occupied by the molecules of a mole of gas. Using this figure, calculate the fraction of the molecule in a container actually occupied by argon atoms. A at STP, B at 100 atmospheres pressure and 0 degrees Celsius. Assume for simplicity that the ideal gas equation still holds. So we have to do the calculation twice. Now here we go again with the fun part of erasing. You know, science is a funny thing. You have to follow the procedure exactly if you want to reproduce your experiment. I've seen an example of poor science on the internet that's been raging ever since this COVID-19 nonsense started. There's a doctor called Vladimir Zelenko who's been saying over and over again that none of his patients ended up intubated. And he was saying that he uses a cocktail of 3 drugs. He's using hydroxychloroquine, zinc, and zithromax. So hydroxychloroquine is an anti-malarial drug. Zinc is just a mineral, and the and the other one is an antibiotic, zithromax. So the antibiotic, I guess, is just preventing infection by other organisms, while the anti-malarial, which is actually also what's called an ionophore. An ionophore is a substance that helps bring ions into the cells. What's actually inhibiting the virus is the zinc. I saw so many scientific papers and scientists coming out saying hydroxychloroquine doesn't work. Yeah, of course it doesn't work. That's not what the doctor said. The doctor said you got to use the hydroxychloroquine with the zinc and the zithromax. So follow the recipe. If they tell you to do an experiment a certain way and then you do it a different way and you get a different result, why are you surprised? You got to do it the way it's written to do it. And I've been posting over and over again on Facebook about this precise point. People are talking about how hydroxychloroquine doesn't work. That's not what he said. What he said is you have to stack it with those other 2 substances, because what's actually working is the zinc. The zinc has to get inside the cell to interfere with
viral replication somehow. But to get it into the cell, you need this ionophore, which wraps itself around the zinc atom and then crosses the cell membrane. If you just give the person the ionophore without the ion, no effect, or perhaps even toxicity. So anytime you take a drug, there's that, you always have that, perform that mental calculation. Is the side effect of the drug going to be worse than what it's meant to fight? So clearly death is not an option. So if there are some side effects, then that's a price you'd be willing to pay if the other option is that you're going to die. And it's important to really, if somebody publishes a study and they tell you this is how you do it, then you got to do it exactly. I remember when I was studying to be, actually I had finished studying, I was already working in the pharmaceutical industry. I remember looking up a paper on how to do an extraction for a certain drug, and I looked up the paper and I followed everything to the letter, and it didn't work. And then I had my eyes opened by the PhD chemist who was working in the same lab. He says, don't you realize all the studies that you can make money from, they actually publish them with errors in the study because they want you to phone the company and ask for permission and the correct version of the study, which they have. They just publish the recipe but with some mistakes on purpose because they want you to pay them to get the real recipe. So you see how it works? That's how it works when money becomes more important than the advancement of science and the good of others. It's sad, but it's a reality that you should know exists. So, if I don't follow my recipe exactly, the board stays dirty. I've got to use a damp cloth to help draw the methanol, the isopropanol away after it solubilizes the marker. See, this one's not damp enough. It's leaving a lot of stuff behind. This one's damp. And it works better. Okay. There we go. Last question then. Let's do the calculation first with a 1 mole sample at 0 degrees Celsius. So assume a 1 mole sample. That's just going to make it easier for us to do the calculation. You can do that whenever you're doing theoretical calculations. This is question number 4, which is based on 1086 from Brown and others, 10th edition. So assume a 1 mole sample at STP. I think they tell you STP in the question itself. So PV equals nRT, and the volume is going to be nRT over P. So divide both sides by P, and you get, so 1 mole times 0.082057 liter atmospheres per Kelvin mole times 273.15 Kelvin, that's 0 degrees Celsius, and 1 atmosphere of pressure. So the volume you'll get from that is 22.4138,696 liters. But the value of B, if you look it up in the text, and I think I showed you, I hope I showed you a picture, a close-up of the text. Oh my gosh, you're staring at a white surface. Okay, sorry about that. The value of B as reported in the text is 0.0322 liters per mole. That's the actual volume of the molecules of the gas. But then they say that it's actually 1/4 of that. So the number they report is 4 times bigger for whatever reason. So 0.0322 liters times a quarter equals 8.05 times 10 to the negative 3 liters. Or if you like, 8.05 milliliters, because you multiply by 1,000 milliliters per liter. And that constitutes, if you take that number and divide it by the total volume, I turned it into a percentage, but you don't have to. if you take the 8.05 times 10 to the minus 3 liters and divided it by the original volume occupied by the whole gas at that temperature, and you multiply by 100, what you get is 3.59 times 10 to the minus 2%. Now, when you redo the calculation, and there's probably not enough room here to redo it, all you're changing is putting that as 100. If you redo the calculation at 100 atmospheres, everything is the same, but you're just changing this to 100. Okay, so the answer you get in that case is V equals 0.224138,696 liters. So it's the same volume except 100 times smaller. So 8.05 times 10 to the minus 3 over 0.224, etc., times 100 now yields an answer of 3.59%. All right, so as the pressure increases, the volume of the gas makes a bigger and bigger impact on the accuracy of the ideal gas equation, because you're compressing the gas into a smaller and smaller space, but at some point you would reach the point where the gas molecules are actually touching. So actually what you have is something that looks like a liquid. So the percentage of the gas volume becomes a bigger and bigger proportion of the volume occupied by the space, the space occupied by the gas, as you compress the gas more and more. All right, that concludes the review of the test. I wanted to do one other thing. I want to review the answer to 2019 A and B. How much time have we used today? Ooh, okay, I'll do A. 2019 A, because otherwise we'll go over half an hour and I know you'll just die. So we go like that. We use the alcohol. You know, I've had this spritzer bottle for years. Yesterday I dropped it and it stopped working properly. Wouldn't you know it? Okay. So on the first one, the first question I gave you for homework was 2019A. It's still a little wet here. So you got to do 2 phases of wiping and then a third for drying. This is the board cleaning protocol 2019A. So you got dichromate Cr2O7 -2 aqueous reacting with iodide anion to produce chromic ions. And what else? Iodate, IO3 minus. Aqueous. So balance that under acidic conditions. First thing is to break it into half reactions. You can leave the AQ part out for now so it doesn't clutter.
So you have 2 chromiums here and 1 chromium there, so you're going to have to put a 2 over here. Then you have 7 oxygens here, 0 oxygens there, so you're going to have to balance that with 7 water molecules. Then by adding 7 water molecules on the right, you're going to create an imbalance of 14 hydrogens, so you'll balance that off on the left side by putting 14 protons. Now you worry about the charge balance. So you got 6 pluses over here, and you got 14 minus 2 over there, so that's 12 pluses. So 12 pluses versus 6 pluses, so you're going to put 6 electrons on this side, so they'll both come down to the same amount, which is plus 6. Okay? Next step is to work on the second half reaction, which is iodide turning into iodate. So the iodines are balanced, you don't have to worry about that, but you have a surplus of 3 oxygens on the right, so you're going to put 3 waters on the left to balance that out. That creates a surplus of 6 hydrogens on the left, so you're going to put 6 H pluses on the right. Now you worry about the charge. There's a -1 on this side, and this -1 balances it off, so you have actually a surplus of 6 positive charges, so you're simply going to put 6 electrons there. Now you got 6 electrons coming in on the left and 6 being used up on the right, so you don't have to write any integers next to the equations because the electrons actually cancel out. They cancel out right off the bat. The 3 waters over here partially cancel with the 7 waters here, leaving 4 waters. And once you've written all that, you can rewrite the whole equation neatly, making sure you don't forget anything. Oh, and I did. Look, I forgot 14H and 6H. So the 14 hydrogens partially cancel with 6 hydrogens, leaving you with 8 hydrogens. Okay, now it's ready to balance. So we start off with dichromate, which is going to be aqueous in the solution, plus 8 protons, also aqueous, plus the iodide ion aqueous, yields 2 chromic ions, aqueous, plus 4 water molecules, plus an iodate. I didn't space it nicely. I had to cram it in at the end. Bugs me when that happens. Anyway, let's double check it, make sure everything is balancing. 2 chromiums, 2 chromiums. 7 oxygens, 4 oxygens plus 3 oxygens is 7 oxygens. 8 hydrogens, 8 hydrogens. 1 iodide, 1 iodine, 1 iodine. It's balanced. Okay, there's your balanced equation under acidic conditions. What you can try now, if you haven't already done so, is do B under acidic conditions, and try getting up to D. You should be able to get up to D tonight. It's not too much work. It's literally about 15 minutes of homework. So try that tonight, and tomorrow I'll give you the answers to B, C, and D all explained. Okay? Good night. Or rather, good afternoon, and see you tomorrow. Bye.